Just kidding. Okay, so Gibbs free energy is the G. Change in Gibbs free energy associated with a reaction as written from left to right. So if we want to be spontaneous, are we looking for less than 0 or greater than 0 for a delta G?
Less than 0.
Less than 0, exactly. There's a couple ways to come up with your Gibbs free energy of a reaction. One of them, we said you can look at the Gibbs free energy of formation of the summation of the products minus summation of reactants. And this is another way, okay? It's related to the enthalpy and the entropy like this, okay? So this is actually one of the things we covered before. If your reaction is at equilibrium, you guys told me if it's negative, it's gonna go from left to right. And if it's positive, it's gonna go from right back to left again. Well, what is it at equilibrium? What's the tipping point between negative and positive? Right. When it's at 0, it's at equilibrium. So actually you can set that equal to 0. You can set Gibbs free energy equal to 0, and actually you can find a temperature at which the system will be at equilibrium. So that's kind of fun. Okay. So yeah, Gibbs free energy negative, it's spontaneous as written. If Gibbs free energy of the reaction is 0, then the system is at equilibrium. If Gibbs free energy is positive, then it's non-spontaneous. Just swing it around the reaction arrows and it will be spontaneous then. So here's one for you. We talked about, what's Q?
Is it just like the snapshot?
Snapshot. Q is a snapshot. Very good. Reaction quotient. Q is a snapshot. So we said we can compare Q, which is a system in equilibrium snapshot, to K, which is your equilibrium constant. And if they're equal, the darn thing's at equilibrium. So we said just a minute ago that if the Gibbs free energy of your reaction is equal to 0, it's also at equilibrium. So I'm going to kind of show you, kind of tit for tat, how Q and K relate to Gibbs free energy. So we said if your Q is too small, then you don't have enough reactants, and it's going to have to go to form, excuse me, if it's too small, you don't have products. Thank you. If it's too small, you don't have enough products, and it's going to have to form products, so it's going to go from left to right. It's what we call spontaneous, okay? And you just told me a minute ago that if Gibbs free energy is negative, it's spontaneous. The last possibility we have is this one, where if your Q is too large and you have too much products, it has to go form reactants. So actually it's the opposite of spontaneous. It's going to proceed from right back to left again. You can swing around, okay, and that's the situation when Gibbs free energy is positive. So we kind of have those two things kind of going on. Well, there's definitely a relationship then between Gibbs free energy of a reaction and your snapshot and your equilibrium constant, your reaction quotient and your equilibrium constant, and it looks like this. One of the things we know about proportionalities is that you can, if you introduce a constant, you can put an equal sign in there. So we have a blue box coming up. Let me look at that, see what I gave you guys. Is this on there? Okay, I'm looking at this. See how that works? So this is your equation sheet. So what this does then is it links the temperature and the equilibrium constant, capital K, there's far too many K's in Gen Chem 2, to the Gibbs free energy of the reaction and ideal gas law constant R. But here, make sure that the value of R you're going to use is the thermodynamic value of R, not the ideal gas law, not the gas value for R. So again, I hate to kind of, just kind of keep pointing this out, but if you want to use this to review, like when you're reviewing, I would become familiar with this. Some years, my final exams are usually very similar, but if you want, I will make sure you have an identical sheet to this. I won't even scramble the equations. So in other words, if you go and look up, you're like, I have no idea what these are. Well, they deal with reaction kinetics, first order, zero order, second order. So you might want to go look at these, and I will give you a sheet just like this when you come take your own test on Monday. And so you'll know how to, I would mark this puppy up. But you can't bring the marked up one. Oh, but you get to bring a sheet. So what you could do, if you're wanting to make sure you got it solid, is take these and put them on your, and explain what they are. Oh, okay, anyway. Cool. Well, this is a powerful thing. Let's do a problem in which we know the delta G, but we don't know the K, shall we? And we're going to use that equation, that relationship. Calculate the K for this complete combustion of methane. Now, earlier on, we actually looked at this and came up with the Gibbs free energy associated with the reaction is negative 817.9 kilojoules. So what do you think, spontaneous or not spontaneous? Spontaneous, yeah. So let's see how we can use that to massage and get to our K. Now some of you hate this, and you're right to not like it. I don't know about hate. But the variable we're trying to get to actually is the natural log of K, okay? So we can rearrange this and say the natural log of K is equal to Gibbs free energy of the reaction divided by RT, and again, the R that we're going to use, you know, is going to be the one that's the units of kilojoules per mole Kelvin. And yeah, don't forget there's a negative sign that we had to carry along. So let's go ahead and plug in the numbers then. That looks like this. The natural log of K is equal to negative 817.9 kilojoules per mole divided by the R value of 0.00831 units of R, kilojoules per mole Kelvin. Also in the denominator is the Kelvin temperature, 298 Kelvin. Now, I didn't say it, but if you go back a slide, how do we know that the temperature is 298 Kelvin?
Because of the knot.
Because of the knot. I think it says standard. Yeah, standard conditions. Very good. Standard conditions is 25 degrees Celsius. If you add 25 degrees Celsius plus 273, you get 298. All right. So what I would do is I'm going to worry about the natural log here in a minute. Actually, you get a value, 3 sig figs of 330. Now this is where, the way I think of it is, see if I can draw on this, I think of it as taking E raised to this power is equal to E raised to this power. By that, do the same thing to both sides. The cool thing about E raised to the natural log of anything is it gives you that thing. And then all we got to do is take E raised to the 330. So K is equal to E raised to 330. We're going to show we're going to give it 3 significant figures. 2.08 times 10 raised to the 143rd power. You're like, ew! Is that more than a Google? Isn't a Googleplex like, or Google's like 10 raised to the hundreds or something? Something like that. So yeah. So what do you think? Is this favor product or reactant side?
Product.
Product. Ooh, by much. Exactly. That's very spontaneous. Okay, so that's it. Now, I don't have these to show you, but I'll look them up and see what I can come up with and push it out there on Twitter. Okay. So, on to part 3. It looks like, dun dun dun, this. So I only want to get so far down the road in this one and then stop. Okay, this actually, remember I said what the title of loosely of the lab on Thursday is something about redox reactions? Okay, redox reactions. Now we've talked about different chemical reactions. We've talked about combustion reactions, you know, about methane reacting with oxygen to form carbon dioxide and water. We've talked about exchange reactions, where you have two ionic compounds exchange cation and anion on the product side. There's another type of chemical reaction called a redox reaction, okay? And that's what we're gonna kind of struggle with now. A redox reaction is one in which oxidation and reduction has occurred. So redox reaction. Some chemistry teachers spend a lot of time in classifying reactions. So this is a classification reaction. Actually, combustion reactions are an example of a redox reaction. But do you see where the redox comes from? Redox is reduction and oxidation. This says oxidation, reduction. It's the same thing, okay? The order doesn't matter. So one of our tasks at identifying that your chemical reaction is a redox reaction, if this hand is reactants, this hand is products, is to see that you have something being oxidized and something being reduced. That's, you know, you have a redox reaction. So in order to understand if something's oxidized and something's reduced, we need to talk about what's called the oxidation numbers just in general. When we get rolling, you can assign an oxidation number to everything in your chemical reaction. Oxidation numbers are associated with an individual atom, okay, as part of a reactant or product. Oxidation numbers. As I was doing oxidation, getting ready for today's lecture, I remember that what this topic reminds me of, although I don't want to throw you off, is the formal limits. Kind of we talked about, we talked about that before. Formal charges, yeah, formal charges. Kind of reminds me of that, but it's a little different. So I'm going to show you the hard way to get to oxidation numbers. Just hold with me, okay? There's an easier way to get to oxidation numbers coming up. But an oxidation number is associated with an atom and is part of your, it doesn't have to be in a chemical reaction, but it can be. It's the apparent charge on that atom at the ionic limit, okay? Again, kind of like formal charges to me. Ionic limit is not the real deal, okay? Ionic limit assumes that all bonds are ionic. You're like, no way. Okay, because we talked about covalent bonds and ionic bonds. Ionic bonds, electrons are transferred. Covalent bonds, electrons are shared. So we're going to assume that electron's going to be transferred, and it's always going to be transferred to the higher electronegative atom. I think that's how it goes. So the charge on each atom, okay, as we look at them holistically, is going to be its oxidation number. Okay, I think I already said that. Okay, so at the ionic limit, electrons that used to be shared are really shared. We're going to associate them with the atom of greater electronegativity. All right, get out your Gen Chem 1 hats. What's the electronegativity trend on the periodic table through the period? Does it increase, or does it increase from left to right, or does it increase from right back to left again? Yeah, electronegativity increases that way. What about in the same group?
Top to bottom. So top down.
Yep, it's like that. Bottom up, yep, and left to right. Yep, that's how electronegativity goes. So we're going to actually end up assigning oxidation numbers to atoms based upon the charge that the atom has at the ionic limit. So here we go. You ready? Oh, one more thing. So kind of like formal charge, it's a little subtraction problem. So I talked about this one right here, this one on the right, okay? What are, for that particular situation, as that atom is fighting itself, what are the number of valence electrons at the ionic limit? Now the first one is the number of valence electrons. Where do you get the number of valence electrons from? the periodic table, yeah, the group. Yep, the group, exactly. Not the period, but the group, exactly. So, yes. All right, so we're gonna take these, 4 atoms, and we are going to come up with oxidation numbers for the chlorines, the carbon, and the oxygen. Now again, this is the hard way to come up with oxidation numbers. There is an easier way, but I want to show you this way first, of course. So we need to say where the electrons are going to go. So what do you think? Between, how many electrons are here in this double bond? 4. Yep. Has 2 electrons and 2 electrons, 4 electrons. So which one's got the greater electronegativity, carbon or oxygen? So I have to take oxygen. Yep. So here in a minute, we're going to see those 4 electrons go that way. What about how many electrons are here? 2. Yep. And so which way are they going to go? That's kind of hard to tell, but come on. Yeah, they're going to go to the chlorine. You're like, because they're different periods, but yeah. Chlorine has a higher electronegativity, so Pauling says, than carbon, so they're going to go this way. So, my gosh, carbon's not going to have anything, is it, at the ionic limit? Yep. So that's at the ionic limit. That's exactly what you told me. Okay, so here goes the little math down here. Remember, it's the valence electrons minus at the ionic limit. So this is what it looks like. For carbon, it's valence electrons of 4 minus, it doesn't have any electrons at the ionic limit. Yeah, carbon's in 4A. Yep, he's double checking. Yep. Let's see. The oxygens are 6A, so they have 6 valence electrons. And in this situation, at the ionic limit, I got that oxygen having 8 electrons. So 6 minus 8 is -2. So yes, oxidation numbers are positive and negative. In fact, do you see where this right here, I mean, 4 minus 0 is 4, but I emphasize plus 4. And that's quite common because you're like, a plus or a negative oxidation number is a big hairy deal. They don't have to be integers, but mostly they're integers. So what do you think about chlorine? What would it be? What's its group number? 7A, so it's 7 minus, how many electrons at the limit? 8. Yep, 7 minus 8, -1. Yep. So over here, on the Lewis structure, we could draw what would we come up with? Plus 4 here. See, oxygen -2. This is a -1 and a -1. Cool. So those are the oxidation numbers for those 4 atoms. What's that?
The limit will always be 8 then, right?
Well, if you have a triple bond, no.
No.
Yep. So not necessarily. Yep. But do you see something interesting that I do too? You see if you take a -1, and a -1, a +4, and a -2, what do you get? Oh, you get 0. Yeah, not the absolute value of. No. They cancel each other out, 0. And that's actually one of the rules I'm going to show you about coming up with, assigning oxidation numbers, is if it's a neutral molecule like this, then when you go, after you're done signing all of oxidation numbers to everything, you should add it to be equal to 0. All sorts of hints. Okay, speaking of hints, and I almost printed these out because I like to refer back to them, but I didn't. I ran out of time and energy. So these can be quite helpful. We're going to see examples of all these rules, but just maybe I'll do examples along the way. So the oxidation number of an element in its free uncombined elemental form is 0. Free uncombined elemental form. So for instance, you could be dealing with sodium, which is kind of a dangerous sort of thing, okay? But do you see where its oxidation number is 0? Okay, magnesium, you guys worked with magnesium solid. Its oxidation number is, that's my version of a 0. That's an important thing, okay? Free uncombined elemental form. Okay, yeah, I'm pretty sure this works too. O2, because oxygen's diatomic, it's usually a gas under normal atmospheric pressures and temperatures. So does it look like it's free, uncombined? It's uncombined, not uncombined with it. It's not combined with anything else. Each one of those oxygen atoms.
So H2 you can see.
Mm-hmm. Yep. So that could be helpful. The oxidation number of a monoatomic ion is simply the charge of the ion. Take on sodium. Sodium +1 charge, its oxidation number is +1. Okay, chlorine, it forms a chloride ion, its oxidation number is -1. See how that works? That's kind of nice. Monoatomic ion, just the charge on the ion. So oxidation numbers just got a little easier. Okay, rule number 3, oxidation numbers of an atom in a polyatomic ion composed of only one element is equal to the charge on that ion divided by the number of atoms in the formula. Oh my gosh, are you serious? I think the example I have coming up, let's see if I can think of another. There are actually 2 that come to mind. Everybody's favorite polyatomic ion. Oh my gosh, that's the mercury 1 polyatomic ion. I hate it, I hate it, I hate it. Okay. But what that says is Hg, covalent bond Hg, all running around with a +2 charge. What this says is that, let's see, is equal to the charge on the ion, which is 2, divided by the atoms in the formula, which is 2. So all this is saying is this one is a +1, this one's a +1. Does that make sense? So my little +1s are my oxidation numbers for those individual. Yeah.
So oxidation number.
+1. I know, it's +1 or +1, but I always has +1 because the -1. Yep, it's just 1. And then the other example I think I have coming up here, so I don't mean to, it's the triiodide ion. Triiodide, like, well, what the heck? Okay, is that not crazy or not? But it's kind of like the mercury 1 polyatomic ion. So we have, I'm going to go ahead and covalently bond 3 of these guys together. They collectively are a -1. This is one of my favorite ones, though. So what this says is you take the charge, which is a -1, and you divide by the number there are, which is 3. So what do you get? -1/3 for each. That's their oxidation number. It doesn't have to be an integer. That crazy or what? I know, it's kind of fun. But if you're dealing with polyatomic ions, whether they're just one atom or whether they're different elements combined together, the oxidation numbers should sum up to be equal to the overall charge. And actually, that's another rule coming up. What else do we got? All right, hydrogen. I think I have a special place in my heart, special slide, special rule coming up for hydrogen and oxygen. Hydrogen, go with it being a +1 unless it actually is combined with a metal and forming a metal hydride. So, for instance, okay, water. This guy is going to be a +1. This guy's a +1. Metal hydride. Sodium, metal. Actually, the name of that is sodium hydride. In this case, it's a -1. We don't do much with metal hydrides. That's the, I don't mean to throw you off, but actually, that is right here. That's the exception, and this is more the rule. Do you see how these water atoms are different than your H2 gas? Because your H2 and H2 gas was in uncombined elemental form. These two hydrogens are part of a molecule, water molecule. So go with +1 unless it's combined with a metal. Okay? That's rule number 4. Rule number 5 deals with oxygen. So just like hydrogen, go with +1. Oxygen, go with a -2. Dang, if I go ahead and bring up my water molecule again then, we are golden. Look at this. What do you think? I'm liking it. Okay? It's a neutral water molecule. You take the sum of +1, +1, -2, the sum is 0, which is perfect. Now notice the exception is in a peroxide linkage as you get with H2O2. Like hydrogen peroxide to me is the most common peroxide linkage. Okay? In that case, it's going to be a -1. Just for kicks, does this work for you? I'm going to go ahead and make my hydrogen a +1. And now this oxygen, I know it's an exception. I probably shouldn't show it to you because we don't really do much of that. But just for kicks, the formula for hydrogen peroxide is H2O2. Notice that if I look to see this neutral molecule, and we kind of do this when we get to rolling, trying to assign oxidation numbers, can you see where I have 2 hydrogens? They're both a +1. And I've got 2 oxygens, they're both a -1. So what is the sum there? It's 0. Since it's a neutral molecule, it needs to be add up to 0. So that's kind of a good check. It's rule 5. Rule 6. This actually is what I've just gave you 2 examples of with water and hydrogen peroxide. If you go about your business signing oxidation numbers, and it's for a neutral molecule, then when you add up those oxidation numbers for all those atoms, their sum should be equal to 0. And then I already did this one too, I think. If you have found oxidation numbers for everything in a polyatomic ion, like ammonium, like NH4+, the sum of all the oxidation numbers of the nitrogen and the 4 hydrogens should be +1, okay? Okay, so let's do some, shall we? Karen, so how do you guys have this? Just like,
It's the same.
get the answers? Oh, let's go around the room. Let's keep you awake. We'll start with, we'll go this way. Okay, 0. He says 0. I'm liking it. Very good. Quaid, what do you think about magnesium? Why 2? Nope. But it's an element, but it's not charged. It's neutral. 0. It is 0. Yep. How about the 4 phosphoruses in P4?
Is that one's not 0, is it? It would be?
It's 0. Yep. It's 0 because remember a rule was in its uncombined elemental form. Uncombined means it's not stuck with anything else, okay? And its elemental form, I guess maybe means that, I don't know, it's neutral. Okay. Okay, on to the next one. What do you think, Mike? 1 + 1. Yep. And sometimes you might be wondering, well, Mrs. Snipes, if I put 1, do I get it right? Yes, you do, but you'll probably see you put +1. Okay. Okay, Quaid, what do you think? The nitrite ion? -3. Oxidation number -3. And we did this one. What do you think about each of the mercury atoms in mercury 1 polyatomic ion?
It's +2.
Each one of them.
Oh, each one is +1.
Each one of them is a +1, exactly. And that's kind of how these slides are written because it says Hg on each one is +1.
Okay, so if we're asked this on a test, you're wanting like for each one, not like the whole combined.
Yeah, yeah.
Combined should always be 0, right?
What's that?
The whole thing combined should be 0, right?
No, the whole thing combined should be a +2 because it's, yeah.
So the charge is the same as the oxidation.
No, the charge will be the same as the oxidation number only if it's a monoatomic ion.
But for polyatomic, the sum of the oxidation numbers will always be 0.
Nope, for polyatomic ion, the sum of the oxidation numbers will be the charge on the polyatomic ion.
For like H2O, it's 0.
Right, that's a neutral molecule.
Okay.
Yeah, if it's neutral, the sum will be 0.
Okay.
But this next one's not neutral. What do you think about each of the 3 I's in? Can't be 1 because you have 3 of them, and then you're going to be running around with -3. So we have I, all running around with a -1 charge. Mm-hmm. Yep. Yep. Is that? And this little exercise we're doing now, how do I say it? That won't be a standalone question. What we're doing now is to try to assign oxidation numbers, and we're going to use those as something else. So let's see what else we got. Now we take it up a notch. these to me kind of end up being kind of like little puzzles. Up here in the corner, I'm going to say the things you can hang your hat on is hydrogen is going to be a +1 and oxygen is going to be a -2. That is for Gen Chem 2, what you can hang your hat on, I think. I think you can. I hope I'm not throwing wrong. Because remember, so the exceptions with regard to hydrogen is if hydrogen is combined with the metal to form metal hydride, it's -1. Exception for oxygen is if it's not normal oxygen, it's forming a peroxide linkage, and it's -1.
So with NH4+, would that be an exception then?
Nope.
No.
So what we do is, and this is what we're going to do more of in Thursday's lab, is we need to take that water molecule and we need to go in kind of above the hydrogens and above the oxygens, say what its oxidation number is. So I already told you over here what it is. So -2 for the oxygen and a +1 for each of the hydrogens. Now I think this is right. You should never, within the same molecule or polyatomic ion, have atoms of the same element that have different oxidation numbers. It's possible to have atoms both on the reactant side or both on the product side of the same element that have different oxidation number, but they'll be in different species. Okay, now the next one gets to be kind of the deduction part. So this is how I get to sulfur. Because I'm like, dude, I got this figured out. I got -2 for each of the oxygens. Come back. And I got plus. It only does what you tell it to do. And I told it to shut up. So what we don't know is the sulfur. I'm going to try to take this off. I did this before. Okay. So +1 right there. So to me, then, you go ahead and write a little problem. And I don't know, this is just how I think of it. I think of my 2 hydrogens, they're both a +1. And I think of my 4 oxygens, and they are a -2. And then I'm going to say plus my sulfur, which there's only one of them, times question mark is equal to 0. I have one equation, one unknown. I know it's a question mark, so the variable x, but.
So if it was H2SO4 plus, I don't know if that's possible, then it'd be equal to 1?
Mm-hmm. Yep.
Okay.
Yep. So we can do this. So let's see how we're going to do it. So I get 3 here, I get -8 here, so that's like we're looking at 5 plus question mark is equal to 0. Does that seem right? Okay. No, I did that wrong. That should be 6, shouldn't it?
Yeah.
Okay, thanks. 6 plus question mark. Yeah, that's better. You buy that? Because I had 4 oxygens, they're -2.
Well, I get
Is S +2?
Yeah, no, S should be +6, right?
Right.
I don't get that plus question mark.
So O wouldn't be -2?
Oxygen is -2, yep, but I have 4 of them. So they look like that. That's my oxygen. Oops, sorry. That's my oxygen.
But you
That's my
have
hydrogen.
2 positive. So wouldn't you just need 1 positive 2?
I have 2 positive here, and I have 8 negative here. So I need 6 positive here to make it 0. +2, a -8, and if I make this a +6, then I'm back to 0.
So it shouldn't just be 6 equals question mark?
Yep. So 6 equals question mark. I'll clear these. I think I can. So you can hang your hat on the hydrogen +1. You can hang your hat on oxygen -2. This whole thing has to be a net 0. So in order for that to work, the oxidation number of your single sulfur needs to be a +6. Okay, let's see what we got for the next one. Again, let's use as our starting place. We know those 4 hydrogens are all a +1. I'm going to put a question mark over my nitrogen. So this is kind of what Mike was saying. There's 1 nitrogen. It is the charge, I don't know. Plus there are 4 hydrogens. It has an oxidation number of +1. Total, it needs to be a +1. Right? I think so. So let's see, -3? Say, so question mark is equal to -3. And that's totally it. So -3 is the oxidation number of nitrogen in that particular setting. Did the oxidation number of nitrogen change? If the oxidation number of nitrogen changes in a chemical reaction, you have a redox reaction. Okay, the last one. Again, oxygen's going to be what? A -2. Chlorine, question mark. So we have 1 chlorine, 1 question mark, plus 2 oxygens, 2 -2, is going to be equal to -1. So that's a -4. So I'm liking, seems like 3? Seem right? Concentrate. Does it seem right for you, 3? Yep, me too. Not just 3, a +3. Okay. So -2 for each of those and a +3 for that 1 chlorine. That work for you? I think so. That's where I wanted to get. So again, you know, those are important tools that we're going to be using in lecture on Wednesday and in lab on Thursday. So don't forget them.